part 2 of how we measure stars, and what we're going to come on to is how we go from an apparent magnitude, that is how bright stars appear, to a measure that's intrinsic to the star. So when we're looking at our apparent magnitude, it really is how bright does the star look to us. So for instance, the sun looks really bright because it's so close. Actually it's not that bright, and we'll look at that. What we want to be able to do is to have a way of using this magnitude scale to express how bright the star really is, and for that we need to know the distance. Why do we need to know the distance? Well, it's pretty clear that the further you are from a source, the fainter it gets. Here you can see the idea that here we have a light source, and if you are 1 radius away, then the amount of light that's coming from the star in this direction is going through this 1 square. But if you're 2 units away, then it's now spread out into 4 squares, and if you're 3 units away, it's spread out into 9 squares. I prefer to think of it as being, the light from the sun or a star spreads out in a sphere, and as it moves out, the same amount of light is spreading through bigger and bigger spheres where the surface area is given by 4 pi r squared, and so it's spread over larger and larger volumes, passing through larger and larger surface areas, and so what you get is that the amount of energy passing through a single unit surface area goes down as 1 over r squared. And so it's just an inverse square law, and so we have that the further away something is, the fainter it is, and it does that by 1 over the distance squared. And so the further away something is, the fainter it is, and we need to account for that if we want to understand what stars are. So that brings us to the idea of an absolute magnitude. So what we want to do is to take how bright the star looks and combine it with its distance. So what we do is we say, okay, what would happen if we did have a celestial sphere and all stars were at 10 parsecs? How bright would they look? And this is just a hypothetical construct. It's just a thought experiment, really, to say this is how bright these stars would be in reality if we compared them to each other. So we move them to a distance of 10 parsecs. So that means that whatever distance they are away, we have to do that distance in parsecs divided by 10 squared. So if it's further away than 10, it will be brighter, and if it's less far away than 10, it will be fainter, and that's how we do the scaling. And so to give you an example of this, here we have Orion, here's Betelgeuse, here's Rigel, here's the Belt, here's the Sword, that's the Orion Nebula. And if we look at these, it's hard to see here, but Rigel is brighter than Betelgeuse. It appears to be about 1.2 times brighter, but it's actually further away than Betelgeuse. So if we take into account the fact that Rigel is further away and it looks brighter, it's actually more than 3 times brighter in reality than Betelgeuse. We'll come back to that later. But I want to go through this in mathematical form. So I want you to consider we have 2 stars. One has an apparent magnitude m, and the other one has an apparent magnitude n. And they have apparent brightnesses, that is their energy per meter squared per second, of little lm and little ln. And so the ratio of the brightnesses, that is how they compare to each other, will correspond to a difference in magnitudes. Okay, so remember that the magnitude difference of 1 is a magnitude brightness ratio of 2.512, the 100 to the 1/5. So we can put this together and say that ln over lm, that is the ratio of the apparent brightness of n to m, is given by this 1 magnitude difference times to the power of whatever the difference in magnitude actually is. And we just rearrange that and we get an equation that looks like this. So that's that equation. We've got the ratio of n to m is given by its magnitude difference in this form. And so I'm going to log both sides so I can rearrange it. So the log on this side and log on this side. Log of 100 to this is just, I can move my power down and do some more rearranging. So now I've got the log of the ratio of the brightnesses is m minus n over 5 times 2, which is 0.4. But now I'm going to move it around again, so I have the difference in the magnitudes is 1 over 0.4, which is 2.5, log ln over lm. And so this is how you're going to do the conversion. If you know that you've got that you can measure the brightnesses, you can work out the relative difference in magnitude, or if you've got the difference in magnitudes, you can work out what their actual brightness ratio is. That's actually important for when we do conversions between units. Now, the difference between the apparent brightness and the absolute brightness, or luminosity, is given by the distance over 10 squared, right? This is just saying that I'm moving everything up to a distance of 10 parsecs to make it an absolute magnitude. And so now if I plug this into here, I've got m minus n is the 2.5 log ln over lm. But now my n becomes my absolute magnitude, and my ln is now my absolute brightness, my absolute luminosity. And if I combine these two, I get that the difference between the apparent magnitude and the absolute magnitude is given by this equation. And I can rearrange this just a little bit. So I have that the difference between the apparent magnitude and the absolute magnitude is simply down to the distance d, but I have this nice log formula. And actually, usually we do it like this. We can measure the distance, say with parallax. We'll come back to other measures of distance. And we can measure how bright it appears. We can work out how bright it actually is. So let's do a couple of examples. Let's think about the Sun. The Sun has an apparent magnitude of minus 27. But it's a very small distance away. It's 1 AU away, which is in parsecs 1 over 200,000. And so, in fact, in terms of the Sun appearing, what would it look like if you moved it away to 10? This is the distance it's at now, and to move it out to 10, you have to multiply by that over 10 squared, and so it would be 10 to the minus 15 times as bright. Now remember that 1 magnitude is 2.51 times brighter, and so we can plug this in, and you can do a log expression to work it out. But what we basically are going to get is the magnitude back from this. So we've got that if you want to be 10 to the minus 15 times less bright, well, 10 to the minus 15 times as bright, then you have to change by 31.6 magnitudes. And if we plug that in, it's fainter, so it goes more positive. So instead of being minus 27, we have to add on that 31.6. And so, in fact, if the Sun was out at a distance of 10 parsecs, it would be visible to the naked eye, but it would be fairly faint. Remember that 6 is the limit of what we can see with the naked eye. Another example is Deneb. It's a famous star. It has an apparent magnitude of plus 1.3, so it's pretty bright. It's up there in brightness. But it's also a very long distance away. It's 450 parsecs away. And so we can do this calculation that if we were to bring it up to 10 parsecs away, it would be over 2,000 times brighter. And again, we know that if we've got 1 magnitude of difference, then the ratio goes up by 2.5 times. So we can plug this in to work out what the difference in magnitude needs to be. And so we've got that for a 2025 times brighter object, it would be brighter by 8.3 magnitudes. And remember, it is getting brighter, so it's a smaller magnitude, so you take it away, and so you'd actually get it at minus 7. And so if Deneb was at a distance of 10 parsecs, it would be brighter in the sky than Venus appears to be. Not as bright as the full moon, but it would be brighter than Venus. It would be very, very bright. Okay, and so we've got this idea that's called the magnitude equation, which we already derived, which gives us the absolute magnitude in terms of the apparent magnitude and the distance. And these are always in parsecs. And we find that when we have a measure of the distance to something, that we have absolute magnitudes, that's true brightnesses, that range from the very brightest are minus 10 in absolute magnitude, and the very faintest are plus 20. Now remember that when we worked this out for the Sun, it was about 5, which is right in the middle, right? It is 15 magnitudes brighter than this one, and 15 magnitudes fainter than that one, plus 5. And since that's 15 magnitudes, and 5 magnitudes is a factor of 100, 10 magnitudes is 10,000, 15 magnitudes is 1,000,000. So we've got stars that are 1,000,000 times fainter than the sun and stars that are 1,000,000 times brighter than the sun. And this is real brightness. This is not the apparent effect of distance. Okay, this takes us to the distance modulus, which is something that if you read some especially older articles in astronomy, you'll find that this is used as a way of thinking about distance. So rather than actually quoting a distance, you've got that the distance is uniquely defined by the difference between the absolute magnitude and the apparent magnitude. Now, one of the things that's really important that we'll get onto very soon is that there are things called standard candles. That is, there's a way to measure the absolute brightness of something by some other behavior. And that means you can say, I know what its absolute brightness is. I can measure what its apparent brightness is, and so I can work out what its distance is. And so this became a way of thinking about distance, was actually the difference between the absolute and apparent brightness in magnitudes was really also used as a distance. And that's just what I just said. So I'm just going to rearrange this also so you can see how this works. So I've just rearranged it so d is on one side, divide by 5, and then up to the power of 10. So if you've got the apparent magnitude and the absolute magnitude, then you get the actual distance in parsecs. So let's go back to our Betelgeuse and Rigel comparison. Remember, here's Orion, here's the belt, here's Betelgeuse, here's Rigel. And here's our magnitude equation. And in this case, we can measure the absolute magnitude. We know how far away it is. They're actually close enough. Remember that Betelgeuse is closer, 152 parsecs. And they're close enough that we can measure this with parallax. And so we've got, but that means we can convert our apparent magnitudes to absolute magnitudes, and we can see that the difference in absolute magnitude is 1.3, and that means that the difference in ratio is 2.512 to the 1.3, or 100 to the 1.3 over 5, which if you stick that in your calculator will come out 3.3, which is what we got before. And that will be the end of brightnesses for now. We'll come back and talk about other parameters.